Hi, this is Discrete Math Notes, section 4.5, Hamiltonian circuits. Previously we did Euler circuits. Now we got to figure out what this Hamiltonian circuit thing is. And so what we want to be able to do is identify Hamiltonian paths and Hamiltonian circuits and do the same for a directed graph, which is a digraph. When we have a directed graph, we have arrows, not just segments. And then we want to analyze tournaments, which are complete digraphs. So some definitions. Hamiltonian path. Path that visits each one of the vertices of a graph exactly once. That's what we want to do. Go to each vertex exactly once. The circuit visits each vertex and starts and ends at the same vertex. And then a tournament is a digraph that results from giving directions to the edges of a complete graph. So, previous section, we did Euler circuits. We wanted to cover all the edges and finish back to where we started from. So let's try that. If I did an Euler circuit here, is that possible? Remember, we count the number of degrees. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 4, 4. So all of these are 4. These are 2. And so all of them are even. If all the vertices are even degreed, in other words, they have the even number of edges that come into it, then yes, we can make an Euler circuit. If it's an Euler path, that is only if we have exactly 2 odd degreed vertices. So you got to remember that. So Euler, yes. And so if I do this, I'd have to zip around here. There's my Euler circuit. Now, I don't know if you want to do that or not because we did that previously. Now I'm going to draw on this because I want to do a Hamiltonian path, Hamiltonian circuit. Now what happens with this is that if I start here, I just want to, by the way, I just want to cover each vertex. So the differences here is Euler might be like the snowplow going through each one of the streets and plowing each one of the streets. The Hamiltonian is representative of possibly a delivery person. You want to go and deliver to each one of these places, and you probably want to minimize actually how many streets that you cover. So you don't want to cover all the streets if you don't have to. So if I start here, I can go to A. Now, if I stop right there, that would be a Hamiltonian path. Now, what's different about Hamiltonian is that Hamiltonian can be yes to path and yes to circuit. With Euler, it was one or the other. With Hamiltonian, it can be both. In fact, if you have a circuit with the Hamiltonian, you also have a path because you just stop one short. So here I stopped at G. Can I finish this up and go back to G where I started from? Yes. I made all my deliveries and I can go back home. That's what the circuit does. And for the path, it was just stopping one short. Okay? Now if I look at this one, can I do an Euler path with this or an Euler circuit? Well, if I start here, I'm not going to be able to finish here. This is odd. And this one is odd, degreed. And so what has to happen is that for an Euler, I'd start at C and finish at D. Now what about if I wanted to cover all the vertices? I'm going back to Hamiltonian again. Circuit, yes or no? Well, I don't think so. I can't really start and stop at the same spot without duplicating one of these edges. So with this, the Hamiltonian circuit is a no. No to the circuit. But what about a Hamiltonian path? Sure, I can do this, and I can do that. That would be, I'm sorry, I just need to stop there. So this would be yes to a path. To make this a circuit, I would somehow have to go back home. So this edge right here, I didn't need for that to be a path. I could have stopped right at E. All right? Now, with the Hamiltonian circuit, you're going to have a lot fewer edges covered than you did with the Euler, just by the nature of the definition. So if you look at what I have written right here, please read that, but it reiterates what I just said about a Hamiltonian path. If I have a Hamiltonian circuit, then I have a Hamiltonian path. If I have Euler, Euler's one or the other. You can't have a circuit that is also a path. Why don't you try number 3 and see if you can find Euler and Hamiltonian path and circuit, and bring that to class, and we'll see what you said about both of those. Okay, so tell me, is it going to be a path or circuit for Euler, and then path and or circuit for a Hamiltonian? Let me go back to this one. If I wanted to write out this path, what I would do is, I said that I started at C. I can just write it out: C, D, A, B, E. This would be my Hamiltonian path. Okay? This is how we write these out. Tell me where you start. Tell me where you finish. No problem there. Okay, let's go to the next page. This next chart tells me how many different Hamiltonian circuits I can have in a K4. We'll talk about this in class, so ask me about the K4 and the different number of Hamiltonian circuits you can have. So in other words, if one person does this, they might get this one here. Another person does it, they might get this one here. However, both of you have a Hamiltonian circuit that you did make up for the K4. Remember that the K4 is the complete graph for 4 vertices. That's the K4. Okay? Now, the last thing we want to do in this section is look at a tournament and build what we call a digraph. So what we have is, in the 1998 basketball, I made this up, so this isn't true. Sorry if anybody's checking me. Basketball IASs, the following results occurred. Make a tournament graph for this. So what we're going to do is, we're going to take this information and we're going to go ahead and build a graph for it. So you're going to start off with each one of these schools. So I have SAS, I have Type A, I have ISB, I have JIS, and I have, that's off the board, there we go. And then I also have ISKL, and then I have ISM. So that's how I graph that. Now what's going to happen is that in a tournament graph, you are going to make a digraph. So you're going to do arrows wherever you have a winner. So this is written with respect to these teams right here. So when I write a W right here, that means that SAS beat Type A, and so on. Type A has an L here, so then that means they lost to SAS. And so this has kind of a reverse symmetry to it. If you go opposite side, a W turns into an L over on the other side. I did that wrong. This one. This one matches up with this one. W matches up with an L. So what happens now is that SAS beat all of their opponents. So when you beat somebody, you're going to draw an arrow to them. So that's what I'm going to do for all of these. SAS beat each one of their opponents. Now if I move on and I look at Type A next, I'm just going in kind of an order who had the most wins. Then Type A beat everybody except for SAS. So when I do this, I don't go back to SAS because they only played one game. So it's going to be a complete graph with no multiple edges. And then if I go to ISB, double check me if I'm doing this right. ISB ended up just beating KL. So I get that there. And then also I have JIS beat ISB, and JIS also beat ISKL. And ISM then beat, who did they beat? ISM beat ISB, and ISM beat GIS, and ISM beat ISKL. Okay, so now this is my graph. What happens now is that if I did a Hamiltonian path here, which vertex would I have to start at? I hope that you can figure out that you'd have to start at SAS. I can never get back to SAS, so I'd have to start here. So this is my starting point. Now I can figure out different paths. In fact, I want you to see if you can figure out a path. So pause this. See if you can start at SAS and get all the way around, following the order of the arrows. Pause this. Now if you notice, I wrote down the order here. Hopefully you tried this and went through this. SAS to Taipei to Manila. Then I have to go over to, down here to Jakarta, and then over to Bangkok and finish at KL. Can you see that KL has to finish last? Because once you go into KL, you can't get out. All right? So, yes, start here, finish here. Now, if you notice, when I did this, if it has a unique path like this, then you have a specific ranking. And that ranking would be, SAS would be 1, Taipei would be 2, ISB would be 5, JIS would be 4, ISKL would be 6, and ISM would be 3. Now we say something else, we say unique. Is this unique? This is yes. Why is it unique? It's unique because there are no ties. There's only one path that we have, and there are no ties. If there's a tie, then I could maybe zip around this thing a different way. So what happens is that if you ever have ties, then it means that you are not unique. Okay? So this is a tournament. The tournament, if you have the path, it will give you the rank order. So here's my rank order there. All right, I hope that this makes sense. It's nice to relate this stuff to real-world applications, and that's what we're trying to do. Thanks. Have a great day. We will see you later.